Welcome, members of the Parliamentary Committee, and thank you so much for gathering today. I'm presenting this explainer as an urgent briefing on the operational realities of our EuroHPC infrastructure. Now, we talk a lot about European AI strategy in terms of high-level policy, regulation, and global competition, right? But today, we are going to look at the actual physical compute substrate that makes absolutely all of those aspirations possible. The decisions we make about this infrastructure today are going to firmly shape Europe's technological sovereignty for the next decade. This is literally the hardware beneath the headlines. So, let's get into it. Okay, let's just dive right into our agenda. 1. Europe's computing substrate today. 2. The factory scale gap. 3. The hardware heterogeneity tax. 4. Engineering litigation tutorial. 5. Hubs, spokes, and antennas. And finally, 6. The summer 2026 deadlines.
Moving right along to Section 1. Europe's computing substrate today, the baseline.
I really want to anchor this entire briefing on one very specific, honestly monumental number, 10 billion euros. That represents the 2021 to 2027 EuroHPC investment. And look, this isn't just funding, this is the public good infrastructure framework that underlies the entire European sovereign AI movement. Through the EuroHPC joint undertaking, this massive investment currently powers 19 AI factories, which have been carefully selected across 21 European countries. We have successfully laid the groundwork here, and the sheer scale of this commitment is absolutely something we should be proud of as a unified body. Just look at our top-tier systems globally. We literally have 3 supercomputers firmly planted in the global top 10. Jupiter over in Germany sits at number 4, deploying an incredible 24,000 NVIDIA Grace Hopper superchips. Then we've got Lumi in Finland running on over 10,000 AMD chips, and Leonardo in Italy powered by roughly 13,000 A100s. These flagship systems operate as the undeniable beating heart of our sovereign AI ecosystem. They are phenomenal achievements of European scientific cooperation. But to understand where we're going, we need to look at what happens when we push these systems to their absolute limits. So, Section 2, the factory scale gap, the trillion parameter ceiling. Now, notice the stark juxtaposition here. On the left, we map out our current AI factory capacity. Our absolute biggest system, Jupiter, maxes out at around 24,000 chips. Now that is a fantastic engine for mid-size models, right around the 70 billion parameter mark. It gets the job done for a huge variety of scientific research. But cast your eyes to the right. Look at the AI Gigafactory target, 100,000 plus advanced processors. That is the massive, sheer scale required to build frontier-class, trillion-parameter models. That's the arena where private U.S. AI labs are currently operating. We are effectively comparing a highly efficient commercial jet to a Saturn V rocket here. The scale is just entirely different. To put this into a concrete, real-world context, consider the Apparatus project. This team successfully trained a 70 billion parameter model on the Alps supercomputer using just over 4,000 GPUs. This is a massive win, for sure. It proves our mid-tier strategy works brilliantly. But, members of the committee, listen closely to this point. We have 0 operationally documented frontier-class training runs on EuroHPC infrastructure. We've hit an empirical ceiling. Why does this matter? Well, because frontier models are what will dictate the future of global AI capabilities, from advanced manufacturing to national security. If we can't train at that scale, we lose our competitive edge. This really highlights the absolute, urgent need to successfully deploy the planned 20 billion euro InvestA facility to build up to 5 true AI gigafactories. Which brings us to Section 3, the hardware heterogeneity tax and fragmented systems. You see, our magnificent computational fleet is actually a highly fragmented mix of hardware architectures. We have a fundamental architectural divide between NVIDIA's CUDA-based ecosystem and AMD's ROCm-based ecosystem. Think of it like asking a world-class orchestra to play a complex symphony, but half the musicians are reading sheet music written in an entirely different language. And even within NVIDIA, we span multiple hardware generations, from the older V100s all the way up to the newest GH200s. Porting software code across these diverse, heterogeneous environments forces European developers to absorb massive optimization overheads. They are paying a literal tax in heavy time and resources that US developers, who often work on massive homogenized private networks, simply do not have to pay. Every hour spent translating code is an hour not spent innovating. Listen to this real-world excerpt from the Apparatus Engineering team's experience report to truly grasp this friction. They wrote, "For specific container image versions, the Python reference implementation of XILU was incompatible with Torch compile, causing JIT compilation to fail, preventing execution." Now, to demystify that jargon for a second, Torch.compile and JIT compilation are basically the foundational translation layers that tell the hardware how to run the math. When that fails, everything stops. The system flatlines. This isn't just a minor theoretical friction point in some research paper. This represents highly expensive, frustrating engineering hours lost just trying to force the code to run on a specific supercomputer's unique environment. Let's move to Section 4, Engineering Mitigation Tutorial, Bypassing the Barriers. Let's walk through a really brief tutorial to see exactly how software engineers on the ground mitigate these barriers. When the Apparatus team hit that catastrophic compilation failure we just talked about, they couldn't just click a refresh button. First, highly specialized systems engineers had to manually dive in and diagnose the incompatibilities deep down within the lowest, most complex layers of that specific supercomputer software stack. Second, they couldn't rely on standard developer tools. They had to manually write highly customized CUDA kernels. Think of these kernels as deeply complex, handcrafted bypass valves designed to force the compilation pipelines to work. And third, they painstakingly implemented these custom solutions. Now, the good news is, for Apparatus, this ultimately achieved a 20% execution speedup. It's brilliant, heroic engineering. But here is the critical takeaway. Relying on this workflow requires a specialized, incredibly scarce tier of engineering talent just to mitigate our own infrastructure fragmentation. We're forcing our brightest minds to be mechanics when they should be drivers. Moving into Section 5, Hubs, Spokes, and Antennas, the Geography of Compute. Look at the dominant hub countries currently hosting our flagship systems: Germany, Italy, Spain, and France. We must acknowledge the structural cause here, with deep empathy for all our European partners. The current member state co-funding requirement inherently favors wealthier nations with massive science and technology budgets. Because a host nation must match EU funding euro for these massive machines, only the most economically robust nations can actually afford to host the top-tier hub systems. This structural reality leaves smaller member states on the outside looking in. They simply can't compete in the procurement process. If we want a truly pan-European AI ecosystem, we have to address this geographical imbalance. Fortunately, we do have a deliberate policy mitigation strategy already in play: the AI factory antennas. Supported by a €55 million EU investment, 13 of these antennas are being deployed across the continent. These act as national gateways. They directly connect smaller or less wealthy member states to those massive, centralized supercomputing hubs we just discussed. These antennas aren't just administrative centers, they're vital connective tissue. They provide high-speed data access, technical support, and the crucial on-ramps necessary to democratize access to the compute substrate. This is a highly actionable policy framework intentionally designed to bridge the infrastructure and equality gaps for smaller member states, bringing them fully into the fold. Finally, Section 6, the summer 2026 deadlines and our closing window. The absolute crucial point to understand today is this highly condensed timeline. On April 15, 2026, the EuroHPC Federation platform shipped its first release to begin harmonizing our disparate network. Right now, in June 2026, we are sitting squarely in the exact target window for the €20 billion AI Gigafactory hosting selection. And looming right around the corner, on August 2nd, the EU AI Act enforcement window officially opens. We literally have only weeks to align our physical infrastructure realities with our sweeping legislative and policy goals. The operational moment of truth is right now, today. And this brings me to my final question for this committee. Will Europe actually deploy frontier-class infrastructure before the window closes? We've established an incredible foundational baseline, but to successfully overcome the hardware heterogeneity tax, the geographical concentration, and the looming factory-scale gap, our next immediate policy moves regarding these AI gigafactories are critical. I hope this explainer has provided a clear view of the hardware realities driving our strategic future. Thank you all so much for your time.